Good evening, good evening. This is the second time up on this stage with Owen, the third time that we've done this all together. And Iwina is actually the third person that we have done this with. So this is really becoming a tradition and it's so much fun. I hope you all enjoy our conversation tonight. Now, Iwina and Owen were briefly introduced by Susan and the team earlier, and you have their bios in the books. But I'll just very quickly leave you with something to think about, which is that Owen, in 2004, so this is almost 20 years ago, was actually an honorable mention, which means that he wasn't bronze, he wasn't silver, he wasn't gold, he was honorable mention.
And a team project.
On a team project. Yet he has come this far and he's really done a lot with what he's learned and really, really impressive. And Iwina, in 2012, you were a bronze winner, although you did your own project. So even if you're just a participant in this program, you can go on to do very, very, very big things. So I'll start our conversation with a question to both of you, and perhaps you can decide how you'd like to answer. So for those of us in the audience who are unfamiliar or less familiar with neuroengineering and neuroscience, could each of you please explain to us in layman's words what neuroscience and neuroengineering are? What's the focus of your work and how mathematics contributed to your work? Age before beauty.
Okay.
Owen.
You're the smarter one. Yeah, sure. So neuroscience as a subject is a field that is concerned about the working principles of the brain. And perhaps it's not a surprise that, or coincidence that two of us become neuroscientists, because among the different biomedical fields, neuroscience is one of the most, I would say, quantitative fields in biomedical science. And so perhaps this is no surprise that some of us who are interested in more mathematical aspects of biology end up becoming neuroscientists, I would say. And for me, what I'm doing now, I started my career in systems neuroscience, but what I'm doing now is very therapeutic-based, therapeutic-oriented. I'm principally interested in working out what kind of changes happen in the aging brain and develop technologies that allow us to hopefully in the future slow the progress of brain aging. And during this process, because very often research is limited by research methodologies that are available to us, so we work on a lot of stuff like improving techniques, for example, for imaging of the brain, like how do we better image it, how do we better extract signal from the images to quantify whether the brain is doing well. And a lot of these are anchored on an understanding of the working principle of the brain, and a lot of that is quantitative model based.
So you said that you developed technologies. Most of us, when we think about technology, we think of electronics and we think of mechanics, but yours is primarily chemistry, is that right?
Both therapeutic space, but also we work on stuff like image analysis, algorithm development.
Okay. On the other hand, Iwina, your area of study is neural engineering, which sounds a lot more technological. Can you explain to us what that is and how math has helped you along the way?
For sure, yeah. Thanks for having me today too. I'm currently a doctorate candidate at Brown University, pursuing my PhD. And what I'm really interested in is to understand the brain itself. It's a huge mystery. Like we are like many decades into understanding the brain, and we still not yet solved it. So I'm really interested in like try to understand more, but from an engineering perspective, because I'm trained as an engineer. And I'm curious to see how we can use technology to help answer questions that we don't know about the brain. So specifically, my research focused on helping people who are paralyzed to like interact with their world and help to improve the quality of life through a technology called brain-computer interface. So it sounds scary at first, but to explain it, basically is to read directly from the neural signals on the motor cortex or in other area of the brain where there are active signals in people who are paralyzed. However, there's like a broken pathway somewhere in the neck, or it could be in brainstem area, or it could be like more severe cases in like ALS, for example. So think of Professor Stephen Hawking, who's a renowned physicist, but then he has suffered from ALS, who can't move his body, but then his brain is perfectly functioning, right? So we're helping people like him who will be able to communicate with the world with much easier tools through BCI, and that is a difficult and challenging engineering feat. Yeah.
So my understanding is brain-computer interface, you kind of roughly split it into sort of an external type and an internal or more invasive version. Which do you focus on?
I focus more on the invasive version. The reason being, in my opinion, you can record more signals and therefore enable deeper connections to the brain and understand more through deeper stimulations.
So think about it. She's inserting sensors into our brain to help those of us who, or not those of us here tonight, but to help humans who are unable to move, who are paralyzed, move or at least interact with the world around them. That's so powerful.
But to clarify that, I don't insert it myself. It will take years of trainings for neurosurgeons to be able to perform that. Yeah.
So to both of you, what do you hope to leave for humanity? What is it that you're doing which you think will have the biggest impact on humanity more broadly?
For me, it would be closely related to what I just said about the research that we've been doing. We want to understand brain aging. We want to develop ways to slow the brain aging process. So hopefully what we can leave for the humanity is that while attaining a deeper understanding of this and developing ways to counteract brain aging, we'll be able to develop therapeutics that helps us tackle the aging population problem and the associated diseases that's going to come like a tsunami. And perhaps if one day one of the things that we do indeed keep the senior mathematicians healthy for longer, we could contribute to mathematics indirectly by keeping their brain young, So that's what I hope to leave behind.
Edwina?
Personally, I like to see people who lost the ability to move their body to regain that through, BCI technology or some therapeutic means. To be able to restore that communication and mobility and independence of and their quality of life in general. Yeah.
So if you think about it, it's not a big leap, and we had this discussion just now over dinner. Owen, Dr. Ko here, is helping our brains live longer and perhaps live forever, if you take it to its logical extreme. And Edwina is actually helping us interact with the world without the use of the rest of our body. So if you were just to have a brain in a jar, theoretically, you could attach motors and robotics. So with these two powers combined, you can imagine what a world we might live in the future. I'll leave it to you to judge if that is scary or magnificent. So, Edwina, maybe I'll do a question for you. You're in dual degrees in electrical engineering and biomedical engineering. How did your educational background, so studying math, having a passion for math, or even the teaching style that you experienced here in Hong Kong, how did that influence your approach to neural engineering? Does it give you do you feel like you have unique advantages over your peers? Do you feel like you think about things differently, or do you just have a more rigorous training maybe? And what has that helped you do in your field of study?
Yeah, I think I would tie it back to when I first joined Hang Lung, where Hang Lung Mathematics Award, where you start with like a basic problem or like a field of study. You dive deeper into the problem and see if we can find a solution. In my mind, as an engineer, I really want to find solutions to problems and how we can solve that through engineering techniques, and I think math definitely plays a huge role in engineering and tools and methods used in engineering. Even though I was trained in engineering, like electrical and biomedical engineering, my focus is deeply into like the biomedical applications. So BCI was super interesting to me because I like to solve puzzles, and the brain is a huge puzzle to me. So therefore, I think applying engineering's techniques or math techniques, actually, the paper that I'm writing right now actually use like a math technique, which is like KL divergence, to measure distributions between neural activities and see how how, like, basically model how the brain changes over time. So it ties back into, like, engineering and math that to me is like the core, as Owen said before, is like the language of the world. Yeah.
Owen, I know you're leading a team specializing in therapeutics development for neurodegeneration.
That's right.
So that's things like Alzheimer's and dementia.
Yes.
Can you elaborate on some of the specific approaches or the treatments being explored by your team that will make us or help our brains live forever?
Sure. We're trying to develop pharmacological approach. So the idea is that in the field, we all read a lot of stuff about anti-aging in the news, in the media, pretty much it's everywhere on the internet. But a lot of that do not have solid science to back their claims. Except there are a very specific class of drug called the mTOR inhibitor that has the most solid experimental evidence today in terms of counteracting a lot of changes occurring in an aging organism. But that approach comes with a lot of limitations due to its both on-target, what we call on-target and off-target side effects. And what we do is to devise an alternative approach that do not have these shortcomings of mTOR inhibition, but attaining pretty much a very similar kind of biological effect in terms of counteracting aging of the brain and the peripheral other organs. And we managed to show that a certain approach would work. And the reason of doing all this is definitely, apart from hoping to keep the senior mathematician healthier for longer, is definitely that we want to, based on this knowledge, develop the next generation of therapeutics for the kind of age-related neurological diseases you just mentioned. Yeah.
So both of you are in neuroscience more broadly. Can you think of ways that you could collaborate? Are there ways that you could work with one another, besides what I just mentioned, which perhaps is a few years down the line? Or are your specific areas of study and research a little bit too far apart to find ways to collaborate?
I think there are definitely room for collaborations, and we love to collaborate in neuroscience and in mathematics as well.
Yeah.
I was thinking in terms of, say, like, we can pinpoint a specific disease, for
Yep.
example, Parkinson's disease,
Yep.
where you attack the problem from the angle of therapeutics.
Aging, biological aspect.
Exactly,
Yeah.
reverse that.
Yeah.
And in the meantime, for the person who's receiving those treatments, they can use BCI to maybe walk again, or restore their movements. Yeah.
And beyond this, we can write a scientific fiction together, based on the idea Adriel just mentioned.
Okay, this is something that I saw recently. Would each of you like to ask the other a question? Because this will be interesting. It gives the audience an idea of how neuroscientists work. So Owen, you can ask Iwina a question, and Iwina one for Owen.
Mm-hmm. Maybe I'll start with some of more of a little bit technical question.
Sure.
You mentioned that in order to attain the most information for controlling, let's say, a prosthetic device, you would go for a more invasive approach. What do you see as the limit of non-invasive counterparts? Like, what's the best we can do? Yeah.
Ooh, best you can do.
Yeah.
I think it all comes down to what do you want to get out of it. Mm-hmm. So there's a recent startup that instead of opening up the brain, the skull, it uses a stentrode where you make a small incision from above blood vessels, and that stentrode will lead all the way to the brain, mm-hmm. where you can basically it's just like one electrode or like a few electrode measurements, but instead of that invasive procedure, medical procedure, it still records something. So even though it's far away from the motor cortex, it was able to pick up some signals that allows the person to maybe perform a click imagery or a click signal. Mm-hmm. To answer back to your question, it all comes down to what the end user wants to do. Mm-hmm. I think for something that that takes more engineering challenge and more difficult to answer questions, it will require better signals, and non-invasive technology may take some time to get to there.
Thank you.
Yeah.
Yeah, I can keep asking.
So for the time being, we still need to insert something into the brain
depends
to
on
get
what
a
you wanna
better
know.
signal,
Right.
right? Okay. Okay. So Iwina, maybe how about you ask a question to Owen about his.
Sure. I'm curious to know what's your opinion on the future. So in 10, 20 years, or even 50 years, do you think it's actually possible to see in your lifetime that someone can reverse the age? And to take a step further, at what age should we think about those things? So should I start like when I'm 30, 40, 50?
Probably later than that. So my personal take on this is that there's a lot of debate on this, but my personal take on this is that aging is sort of an irreversible process. We can slow down the progression of specific aspects of aging process, but it's practically, I think, impossible to reverse the thing. So the best we can do is to devise approaches to slow certain aspects that are most relevant to disease onset or disease development. That would be the most practical and pragmatic, I would say. Yeah.
So should I be worried now?
No, you don't have to. Probably in another 30 years.
Okay, so I have a question for Owen then. If that's the case, at what age would you stop the aging of your own brain if you had the choice? Would you stop it at 20, 30, 40?
Probably 20, I'd say, yeah. Yeah, it's a very personal thing. I just kind of feel that I was smarter when I was 20 than now.
Yet you're still doing so many impressive things. Okay, so I'll try to bring it a little bit more back to the audience now. What do you think we can do to further the awareness and education of the younger generation about neuroscience and neural engineering? I'm sure some of us here have heard about these concepts before, but at what age do you think we can start introducing it to either high school or primary school or secondary school? And what else do you think we can do to further your cause?
Maybe anywhere between the primary school, high school with a good starting point. And I definitely think that, so the things like you guys are doing, this venue, this opportunity provided by Hangno Method Voice is already an excellent example of disseminating messages and sharing some of what's going on in this field of neuroscience and neuroengineering to high school students. So perhaps more publicity, more other similar public events would definitely be beneficial as well. Yeah.
Yeah, I would definitely agree. Earlier the better. I mean, Hong Kong does a great job at promoting STEAM and STEM science, even to the young age students in primary schools. I know it sounds like scary to let's learn neuroscience, but then say in the US, people actually they started really early on just to learn about what are the basic understanding of neuroscience? Can it be an easy toy model to learn about it? And yeah, it doesn't have to be difficult, but
it sounds scarier to me to insert a chip into my brain to
not
learn
that
about
far.
neuroscience. Okay, so lastly, what advice would you give to the students here tonight? Those who are not yet even in college, who may not even know where they're going to go to college, what they're going to study, less what they're going to do in life. You're both very, very highly accomplished scientists and on your way to be scientists. What advice would you give to them? How should they think about their career, about their studies, about their future?
I would say don't limit yourself. Don't limit by your own imagination. There are many paths that you can go into different areas of studies. People change career in the middle of their lives. If you can live forever, you can change your careers any number of times, right? So don't be limited by your own imagination. Just dream big and work hard. Yeah.
Yeah. Yeah.
Owen?
I've said something very similar 5 years ago when I was first given the opportunity of being on the stage to share. I said that I think mathematics is the new English, and I stick to that. And I also share that I still think that picking mathematics as your major in undergraduate studies is an excellent choice. But on the other hand, if any of the smarty pants sitting here today want to ditch mathematics and come to medical school, talk to me.
So mathematics will be the new lingua franca going forward. Dream big and work hard. I think these are excellent pieces of advice for all the young people here. So again, thank you so much, Iwina. Thank you, Owen. And let's give them a big round of applause.
Thank you.
Thank you, Owen, Iwina, and Adriel, for a very stimulating discussion. May I now invite Adriel to present a small memento to Owen and Iwina as a token of our appreciation. Thank you very much.